everyone, and welcome to another video. I'm very excited for the discussion today because today we get to combine two of my favorite topics, namely flight mechanics and optimization, to solve a really neat engineering problem. The problem we want to solve today is how to trim a dynamic model. This process is also sometimes referred to as finding a trim point. We'll get into exactly what that means in a second, but at a high level, this means finding appropriate states and controls to get a system to operate at a desired condition. Now, finding a trim point of a system is a very common engineering problem, and the strategy we're going to outline today is applicable to a wide variety of dynamic systems and trim points. That being said, you know me, I like to use concrete examples to illustrate ideas, so the specific system we're going to look at today is trimming a twin-engine aircraft, and the condition we want is having this thing fly straight and level. Now, to make this happen, we need to understand the dynamics of the aircraft, so please make sure you've watched these two videos where we outline the equations of motions and generate a MATLAB Simulink implementation of the vehicle. Then, to perform the actual trimming process, we're going to leverage numerical optimization techniques, namely unconstrained numerical optimization and the penalty method. Now, these ideas were outlined in these previous three videos, so also please make sure you've watched these before continuing on. Now, if you've completed all those prerequisites, we finally get to combine all these ideas together and get this aircraft operating in the condition we want. So, if you're more excited than I was when they added unicorn marshmallows to Lucky Charms, let's jump over to the whiteboard and get started. Alright, so one of the first things that we maybe want to talk about is let's introduce the nomenclature of trim and equilibrium points. And we're going to see that these are not necessarily the exact same thing, okay? So to start this discussion, remember, we're talking about a dynamic system, right? And the dynamic system is probably going to be governed by equations of motion, something like, let's assume that we can get this in explicit first order form where you have x dot is some function of x and u, right? So this is our general nonlinear equations of motion. Again, f is a vector valued function that you give it the states and the control at any given time, and this function will return the state derivative dot, right? So this is a fairly general nonlinear representation of equations of motion, right, for some kind of system. Now, right now, we said that the idea with a trim or an equilibrium point is I want to find what is the state vector and what is the control vector that will place this system in some kind of operating condition that we find desirable, okay? One thing that you might consider is a very popular one is a lot of people are interested in finding how can I find the magic value of the state vector and the magic value of the control vector such that the state derivative dots are equal to 0. Because if that happens, right, if you find the state and the control that make the left-hand side equal to 0, it basically means the state is not changing with time, right? That means the system is not going to move, meaning it's going to sit there statically or it's going to sit there at equilibrium. So the definition of an equilibrium point, in other words, equilibrium point is basically, and actually maybe we should say equilibrium points plural, right? Because we're going to see there's not just one. Basically, these points, as we can define them, let's just write this down. So equilibrium points, these are kind of defined to be basically all of the state values, and again, these states could be in our, let's say you have n states, okay? And all the control values, and again, let's say you have m controls, okay? Such that f of x u is 0. And maybe let's put a bar on that to make sure that we denote that this is a vector, right? So what you're saying here is equilibrium points are defined as whatever magic values of x and u such that when you plug it into the equations of motion, x dot is equal to 0. And maybe let's put a little not symbol on these. How about? To just denote that these are equilibrium points, right? They have the magical property that if you can find these values, the system will, if you can find the values and place the system at this state and with this control input, it's not going to go anywhere at all, right? So again, the idea with an equilibrium point is, let's write this down, right? If you are at an equilibrium point, right, then the system will stay at this point, right? And again, we see that the reason we call them equilibrium points plural, right, is because if you look at this long enough, right, how would you find an equilibrium point? right? What you're basically doing is you need to solve this equation over here, right? So let's say, how about finding equilibrium points, right? It's basically solve this equation, right? All you have to do is solve f of x naught u naught is equal to 0, right? So this is n equations, right? So f here, this is n equations, right? And how many unknowns or how many degrees of freedom are there? You are picking all of the states and all of the controls. So it's n plus m degrees of freedom, right? Or variables, if you want to think about it that way, right? So usually this is an under-constrained problem in the sense that there are more degrees of freedom than there are equations. So the solution space is usually infinite, right? Well, not usually. Maybe I should be careful with that adjective of usually, but it can be infinite here, right? Because you have more degrees of freedom than you have equations. Okay, so this is the idea of an equilibrium point. Maybe let's go do a really quick example of finding an equilibrium point of a simple spring mass damper system. All right, so let's look at an example of a really simple spring mass damper. And again, I think if you're this far along in our discussion of flight mechanics and optimization, you've probably seen spring mass dampers a lot before. So I'm not going to go through the whole derivation of this. I think everyone is comfortable with the sense that if I've got a single spring mass damper system here, which is moving in the horizontal direction, and I measure the position from equilibrium, I can define the states as being the position and the velocity of the block. The control input is there's one force on this I'm labeling as T, and then if you go ahead and write the equations of motion for this system, basically applying Newton's second law, you'll come up with this set of equations of motion, right? And this right here, this is our f of x u, right? You give it the state, x1 and x2 here, you give it the control, u1 here, and this will basically give you the x dot, right? So here's the f of xu. So what we're interested in doing right now is let's just go ahead and try to find a equilibrium point for this system. So if I want to find the equilibrium points, and I guess I always, a lot of times people just call it an equilibrium point, and again, I always want to hammer home that it should be plural, right? There are multiple equilibrium points for many systems. Okay, so if I want to do this, all we have to do is just solve f of x u is equal to 0, right? So in other words, I just need to solve this equation over here, x2, and then 1 over m u1 minus k over m x1 minus c over m x2. This has got to equal 0, 0. Right? So from the first equation, we immediately see that we have the requirement that x2 has got to be 0. Okay? So we can box this up. This is one requirement that we see immediately from this first row. Now, substituting that into the second row, we now have what? We have 1 over m u1 minus k over m x1. Got to equal 0, but we said this x2 has got to be 0 from the first relationship. So this is what we end up with. So we see that actually right here we end up with one equation and two unknowns. So really there's a relationship between x1 and u1 that will yield an equilibrium situation. So by basically solving for that relationship, you can, let's solve for x1. We basically end up with x1 is equal to 1 over k times the mass. No, sorry, whoops, sorry, excuse me, times u1. Right? So here's the relationship for our equilibrium point. So we can see here that the equilibrium point that we achieve for this system here is x1 just has to be 1 over k times u1 and then 0, and then the u0 is u1 can be free. Okay, so as long as we satisfy this, these are the equilibrium points for the system. And again, this makes good physical intuitive sense, right? What this is basically saying here is that at equilibrium, what's going on? The spring force, right? Which the spring force, like if we write this down, the force by the spring, right? Isn't that k times x1? Right? It's the spring constant times its deflection, right? And what this is basically saying is this spring force has to equal u1, right? Isn't that what this relationship is basically saying here? u1 is equal to k times x1. So at equilibrium, the spring force exactly equals the force that you apply to the block, so the block is going to sit there and not ever move, right? So this is our solution for our equilibrium point. And again, it makes physical, intuitive sense what's going on. And you can see the process is pretty darn straightforward to find this equilibrium point, right? All it boils down to is solving your equations of motion, x dot is equal to 0, okay? Now, that being said, the reason we were able to go through this process, right, is because the equations here, or our f, right, this is actually ridiculously simple, right? This is about the easiest dynamic system you can ever come across, right? If you have the dynamic equations of like an aircraft, like we talked about earlier, this f is much, much, much more complicated, and actually doing this step of trying to solve f of x u is equal to 0 is definitely non-trivial. So we might think, how could you go about actually solving this? Is there another way, instead of trying to analytically solve this, what's another approach? Let's think like, how would a pilot actually do this? Let's say a pilot is flying, you've got your aircraft and you're flying along, and you want to find a condition of, I want this thing sitting at a condition and staying there. Like, for example, straight and level flight. I just want to be able to have this thing cruise and sit here, not moving, and it's just going in one direction, and that's it. Well, what they would probably do is they'd fly around, right? The aircraft is probably wiggling around. They would jiggle the control surfaces, right? They might perturb the elevator just a little bit, try to get the pitch motion stabilized, and they might do the same thing for the aileron. And if they're very careful with all of those control surface deflections, and they make small minor corrections and watching the results, they might be able to eventually trim the aircraft into this condition, right? So that's what I want to look at now, right? That's the intuitive way that you think that a pilot might do this, but right, as engineers, we don't actually want to come up with a system that requires you to go fly the aircraft, right? We want to be able to do some sort of numerical routine that will allow us to work with the mathematical model, right, and find this trim point, rather than having to go up and conduct these costly, expensive flight tests, right? So with that being said, give me a second to erase the board, and let's think about what if instead of looking at this really darn simple example, we had our full 6 degree of freedom nonlinear RCAM 2-engine aircraft model. All right, so let's now look at applying this idea to our RCAM model and trying to find a condition for steady state, straight and level trim flight. So to refresh your memory, with our RCAM model, we had 9 states, right? U, V, W, P, Q, R, and phi, theta, psi, and we had 5 control inputs, right? The aileron, the tail, the rudder, and 2 engines, okay? So the equations of motion for this RCAM model that we developed in our previous discussion was basically, again, it fit our nice form of f of x dot is equal to f of xu, right? Something like this. So the problem, maybe let's state it right now, what we want to do. The problem here is I want to find the x naught and u naught, right? I want to find the state and control vector for steady state. Maybe I'm just going to abbreviate this, SS, steady state, S and L, straight and level flight. Right, so this is a very high level idea of what I want to do. I want to get the aircraft so it's flying, and maybe I've got my little prop right here, right? What we want for the aircraft, again, this is not a twin engine aircraft, but it's just an aircraft. But we want this thing flying straight and level with trim flight. So I want to get it so that the aircraft is flying where it is, the wings are level and it is just going straight. It's not climbing, it's not descending, it's not turning. It's just, it's literally like, it's a set it and forget it kind of setting, right? You want to be able to put the aircraft at this state with these control surface inputs and set it like that Ronco, what is it, rotisserie oven thing, right? It's just going to go, 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 and it's just going to fly along like this, and it's going to do that forever, right? That's the idea. That's what we want to do. I want to find this for that condition, right? I want to find the state and controls that are necessary in order to achieve that flight condition, okay? So one thing that we maybe should note here is, if you think about this long enough, let's just make a small note. At this point, there's no real difference between a state and a control, right? They're both sort of degrees of freedom, or they're variables we're trying to solve for, right? They're decision variables. So we should say that, note, from a solution standpoint, right? Both x and u are decision variables. Right, or degrees of freedom, however you want to think about them. So maybe to make our life easier, let's just call z is our vector of decision variables. Let's just stack x and u on top of one another, right? Because like we said, at the end of the day, what we're trying to do is I'm trying to pick these magic 9 values and pick these magic 5 values. So really, it's just picking a magic 14 magic numbers that will achieve this, right? So maybe what I can do is let's just revise this slightly. So what I can say is x dot is f of, let's just make this a function of z, right? Right? And then all I'm trying to do is, again, I'm still trying to find these 9 numbers and 5 numbers. So really, I'm just trying to find 14 numbers just to say z naught, right? I'm just trying to find 14 values. All the U, V, W, P, Q, R, phi, theta, psi, aileron, tail, rudder, and 2 throttles, that will get me steady state, straight, and level flight, okay? So that's the game plan. Now, what we should do is, let's see if we can translate. This is sort of the English sentence describing what I want to have happen. How can we translate that into mathematical equations or constraints, okay? So let's think about this. What does this adjective here, steady state, mean? Steady state means, steady state, if you think about it, just means it's not, nothing is changing, right? That everything has reached steady state. Dynamics are not evolving any longer. It has reached an equilibrium point, right? So in other words, this adjective steady state basically says I need x dot to be equal to 0. So let's write that down right now. So I'm going to call these, let's call them relationships, or later we're going to see these are going to turn into constraints. However you want to think of them, or equations, right? But equations 1 through 9 are basically x dot is equal to 0, right? This is basically the steady state constraint. If you can get this to happen, if I can get x dot equal to be 0, that basically means you are in an equilibrium point, as we talked about earlier, which basically is the exact same thing as steady state, right? So, and again, these, remember, this is 9 equations, right? It's solving f1 is equal to 0, f2 is equal to 0, all the way down to f9 is equal to 0, right? And, you know, we'll take a look at what this equation looks like in a second, but just remember that this is actually 9 constraints or 9 relationships all at the same time. Okay, let's think, what else can we do? Steady state, straight, and level trim flight. Well, we can probably pick an airspeed that we want the aircraft to be flying at. So let's put down, how about a constraint number 10? I want the airspeed, let's call it VA. Let's make this 85 meters per second. So that's not explicitly stated in our English sentence, but all of you who are pilots or have flown an aircraft know that you can trim the aircraft so that it's flying slow, medium, fast, and anywhere in between. So let's just pick an arbitrary value, okay? So what this is doing is we're putting a constraint on airspeed. I want to be flying at 85 meters a second, okay? What else? Okay, how about, let's do the constraint number 11. Let's do this, how about this thing, level. Yeah, straight, let's combine actually. How about straight and level? What does that mean? Straight and level. So you've got your aircraft. Usually what this implies is, again, we want a combination of, I don't want the aircraft to be gaining altitude, and I don't want it to be losing altitude as you go through this maneuver, right? I want it to maintain the same altitude, okay? So there's a couple of ways we can enforce this idea of same altitude, okay? The one that I'm going to propose right now is, let's put a constraint on the flight path angle gamma here. So gamma is equal to 0, okay? 0 radians, right? So again, the flight path angle, for those of you who have taken elementary flight mechanics, is basically the angle that the center of the angle that the velocity vector of the center of gravity of the vehicle makes with the local horizon, right? So if that is 0, it means it's, you know, the aircraft could be, it could be pitched up at a severe angle, but it's going in such a fashion that the CG, its velocity vector is perfectly horizontal, right? So it's not gaining or losing altitude, right? That's the idea with this flight path angle gamma. So let's just go ahead and enforce that. This is part of the straight and the level constraint. And in fact, straight and the level, it means a couple of things, right? We also want no side slip. So let's do this. So 0 meters a second. So I don't want the aircraft, you could potentially get the aircraft moving along at the same altitude if you were to like crab or crank the rudder over and slip your way through. So I guess this is kind of hard to see. Maybe I'll do it into the camera, right? We want an action like this where it is just flying and coming straight at the camera or straight in space. We don't want it where you're crabbing off to the side and the aircraft, you know, is like going something like this in a severe side wind, right? Or crosswind. We don't want something like that. So let's add a constraint here on V. So V equals 0 is going to help us try to enforce that. And then finally, let's do 13 here. I want the wings to be level. I don't want any bank angle. So let's put a constraint or a relationship on bank. Okay, so all three of these together kind of make up this idea of straight and level. Right? That's what we're trying to capture. So mathematically, when somebody says straight and level, this is our mathematical interpretation of what it means to be straight and level. Okay? Now, the last thing that we want to add, let's add a 14th constraint here, or a 14th relationship, and that is this. I'm going to write it down, then we'll talk through it. So I want psi is equal to 0. Basically, if you think about what this means heading north. Okay? So this technically this means I need the heading angle pointing north, not the course angle. There's a slight difference that we're going to get into later when we start discussing navigation equations. But long story short, you can get this aircraft flying straight and level if I'm flying east, or if I'm flying north, or I'm flying any other random direction, right? All we're doing here is we're nailing down and specifying which direction I want the vehicle heading. So in this case, I want the vehicle heading due north. So if north is that way, I want a solution so that the aircraft is pointed and flying in that direction while not gaining or losing altitude and having the wings level and flying at 85 meters per second and all this kind of stuff, right? So mathematically, these 14 constraints are sort of our mathematical representation of this English sentence here of steady state, straight and level trim flight, okay? So great. So at this point, we're actually in a pretty good situation, right? If you think about this long enough, because what are we trying to do? We said there are 14 values, right? What I'm trying to do here is find these 14 numbers, right? Or find a set of 14 numbers such that it satisfies 14 of these relationships, right? So you could think about this as, you know what? I got 14 equations, I got 14 unknowns or degrees of freedom. Heck, do exactly like we did with the spring mass damper, right? Just start solving these relationships and see what they end up with. Well, here's where we're going to hit a bit of a clang. Let's just think about this first one, trying to solve equations 1 through 9, trying to find out what is going to yield steady state behavior, right? What this means is we have to solve, so to get equations 1 through 9, right, we need to solve, right, f of x, or I guess f of z, right, using our new notation, right? There's just this decision vector z is equal to 0, right? That's all you got to do apparently for equation 9. But you know what? In the interest of completeness, let's look at what this equation sort of looks like. Let's jump over to PowerPoint, where I've actually compiled what do all these f's look like for our RCAM model, and see what it looks like. All right, so here we have the equations that we talked about earlier. So again, up here in the upper left, this is our x dot is equal to f of xu. And just to make this a little bit easier to display on one screen, what I've done here is we're in an interesting situation with our RCAM model in the sense that we can write these dynamics in what's called control affine form, or in the sense that we can break off and pull out the control vector out here and multiply it by this matrix G. So this matrix G right here, I'm showing you here down at the bottom, it's already non-trivial. You can see that it's got x's buried all over the place. It's pretty big, it's pretty complicated, but luckily what this allows us to do is write the G on one page. We're going to see later on down the road that it's really these f terms that are really complicated, but you can already see that this is getting a little bit out of hand in the sense that this little thing of trying to solve x dot is equal to 0 or little f is equal to 0, I'm already going to have this complicated g's. Now let's start looking at what are each one of the components of this big f matrix, right? There's going to be an f1 through f9. So let's just flip the slides, and here's what f1 and f2 look like for our RCAM model, and you can see they are complicated. And if we keep going for f3 and f4, they're even worse. F5 is the worst of them all. Look at this thing. Can you imagine trying to solve this thing simultaneously? F6 is also bad, and surprisingly, F7, 8, 9 are actually not so bad. And I'll actually leave this as an exercise to the reader of why X7, 8 or F7, 8, 9 are not so bad and fairly simple. But long story short, again, I just wanted to flash this up for completeness just to show you that these equations of motion that we're dealing with our RCAM model are very complicated and non-trivial. So trying to solve these things, like let's back up all the way to the first slide, trying to solve this x dot is equal to 0 means solving these 8 pages, or however many, 5 slides, I guess, worth of complicated equations simultaneously for those 14 values, right? The 9 states and the 5 controls that are going to allow this to be all equal to 0 magically. So clearly this is intractable if we try to attack it from an analytical perspective. So let's jump over to the whiteboard and see if there's a numerical way that we can approach this.
All right, so we saw that trying to solve these 9 equations for these 14 unknowns is intractable in this case. So you know what? Trying to do all 14 simultaneously, all 14 of those equations for these 14 variables simultaneously and analytically is even more intractable, right? So that's not a valid way to go about this. Luckily, if you remember our previous video where we discussed how you can use optimization techniques to try to solve n equations for m unknowns simultaneously, right? We can apply that directly right here. So what we're going to do is, instead of trying to solve them analytically, let's try to solve them in an approximate numerical fashion using the optimization penalty method. So in other words, what we want to do is, let's come back to this problem statement, okay? And let's just slightly revise this. So again, we still want to find the z's for steady state, straight, and level flight, but you know what we could do is, the other way to pose this question, right, is, let's go ahead and get ourselves a little bit of room, right, is what we could write is another, let's call this maybe P approximate, right? We could try to minimize a cost function, F0, that is, let me see here. How do we want to do this to make this consistent with our previous notation? We could try to minimize this cost function such that these are all satisfied, right? So these are like F1 through 14 are equal to 0, okay? And I guess we need to make one slight rejiggering, I guess, of this function right here. I'm going to move the 85 to the other side just so I can get everything equal to 0. So in other words, I want to restate constraint number 10 as basically VA minus 85 is equal to 0, right? So now we've got all of these are basically 14 equality constraints, right? So what we've got here is we've got well, actually, maybe, sorry, this is not the approximate problem yet. This is the exact problem, right? So this is another way to restate this problem, right? All this is saying here is, here's an optimization framework, a constrained optimization problem, right, with 14 constraints. Here's my 14 constraints, okay? Now what we're going to do is, let's apply the penalty method, right, to basically move these hard constraints into the cost function. So in this case, we see that there really isn't a cost function, right? This can be a constant, right? And the easiest constant to use, I think we've seen in the past, is just use 0, right? So again, this is just a find the feasible set problem, which is the same thing as solving all these equations simultaneously, but that is too hard to do. So instead, our P approximate problem, right, is we're going to now minimize F0 hat, right, which is going to be F0 plus all of these penalty terms. Now I'm going to write the penalty terms as this. Let's write this as Q transpose HQ here. And in this case, where Q, this is going to be a vector of basically all of our constraints stacked up. Okay, so this is going to be X dot. This is going to be the first 9. So if you think about this is actually 9 elements, right? And then we're going to stack in VA minus 85, right? And then we've got gamma. Where that was gamma, this is sidewards velocity, so that's actually x2, right? And then this phi, I think, was x7, and then psi was x9, okay? Okay, so this vector right here, it's a what? It's a 14 by 1, right? Because this is 9, 10, 11, 12, 13, 14, right? So it's a 14 by 1 vector. So it's basically, we're stacking up all of the constraints, right? All these are constraint functions f1 through 14. We're just going to stack them all up in this vector Q. And now, this H matrix is basically our matrix of penalty parameters. Okay, and the easiest thing to start with is I would recommend starting with an H matrix of something completely diagonal and make this thing, let me see, I guess we need to use MATLAB notation of this. So diag of alpha 1, alpha 2, yada, 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 all the way up to alpha 14. So these are the penalty parameters. And again, I'm going to assume that you're familiar with the idea of the penalty parameters and the penalty function because you watched our previous videos. This thing is basically a 14 by 14 square matrix where you have these alphas on the diagonals and zeros everywhere else, okay? So by the time you do this, and again, let's look at this. Maybe we can get rid of this because we said our original cost function is 0, right? So really, this is the cost function that we're minimizing in the unconstrained approximate problem where we've now moved all of the penalty functions, and the penalty parameters up here into the cost function. So if we look at what this thing looks like, maybe what we should do is let's write out just a few terms just so we can get a feel for what that cost function looks like. Okay, so this cost function f0 hat, right? If you were to go about and do this operation, you're going to see this is going to end up looking something like an alpha 1 x1 dot squared plus an alpha 2 x2 dot squared plus yada 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 all the way up to alpha 9 x dot 9 squared plus, okay, and then we're going to get this term. We're going to basically get an alpha 10 times VA minus 85 squared plus an alpha 11 gamma squared plus alpha 12 x2 squared plus alpha 13 x7 squared plus alpha 14 x9 squared. Yikes, there we go, okay? So this thing is kind of interesting. A couple of things that we might want to note here. Note, this is basically, it's a quadratic in the penalty functions, right? It's a quadratic in these, right? So let's say this is a quadratic in the penalty function, right? Because it has the form alpha something times the penalty function of x squared, right? Plus yada, 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 plus all the way up to alpha 14 times penalty function 14 squared. Something like that, right? It has this quadratic form. But if you look at this thing, right, it's actually, we should make a quick note here that this is not quadratic in Z, right? And Z we said was our state and control, right? Because if you look at this thing, things like VA, right? VA, this thing, the airspeed, this is x1 squared plus x2 squared plus x3 squared square rooted. Then you square that whole thing. So really, if you wanted to look at what does this f0 hat look like as a function of Z, right? This is actually pretty darn complicated. Right? And actually it's even more obvious to see that because these terms, x1 dot all the way through x9 dot, those are the ridiculous functions that we stuck in earlier. So, or that we showed in PowerPoint earlier. So this thing is definitely not quadratic in Z. It's a really freaking complicated function in Z. But in terms of the penalty functions, it is quadratic, right? And what's nice about this is, again, if you look at this cost function, what's awesome about the cost function, let me erase this, we don't need this guy anymore, is that we can also note here that it's got the behavior that we'd like, right? In the sense that f0 hat of Z, this thing is greater than or equal to 0 for all Z, right? No matter what value of Z you stick in here, you always get something that is greater than or equal to 0. And in fact, the only time you get this thing to be equal to 0, this basically happens if and only if, all constraints are satisfied, right? And what I mean by all constraints are these 14 right here, right? If all these constraints are satisfied, that cost function here evaluates to 0. So the game plan now at this point should basically be, we should run over to MATLAB and see if we can use fmin search to go ahead and implement this. Now, a couple of things we should note. Let's make sure that we have everything we need to make this penalty function. So I guess we need to make sure we can describe VA as a function of the states. Okay, so maybe let me make a quick side note. Or are we going to not run out of room? We've got enough room right here. Let's just make a quick note here. I need to basically come up with a relationship to VA as a function of all the states. And like we said, that's pretty easy. That is x1 squared plus x2 squared plus x3 squared. Okay, now gamma is a little bit different here. Gamma, the flight path angle, what I'm going to use right here actually for this formulation is, let's go ahead and say that gamma is going to be your pitch angle minus the angle of attack. Okay, and here, again, you got to look at this. Pitch angle, luckily that is already one of our states directly, so that is no problem. So this guy is x, crud, where was it? I just lost it. U, V, W, P, Q, R, phi, I think this is x8, right? That's x8. And alpha, angle of attack, this is a tan 2, right? We talked about this earlier of x3 and x1, right? Now, the other thing we should maybe note here is just, let's put a little asterisk here and just say a little warning. Warning, this is only valid for wings level. So if your bank angle is 0, this is a good formulation for the flight path angle of the center of gravity of the vehicle. Later down the road, when we actually start studying navigation equations, we'll come up with a much better, more robust expression for gamma. But this is going to serve our purposes okay in this situation because we've got this constraint enforced where the wings are going to be level. If the wings were not level, you could potentially run into problems here if you use this type of formulation. But in our case, we're okay. I just wanted to bring that to your attention right now and file that in the back of your head so that we could do this. What else should we do? Maybe mention... I think this is all right. Okay, so let's go ahead and, yeah, we've got everything we need. Let's go over to MATLAB, get this cost function implemented, and then throw this thing at fmin search and see if we can get it to find a solution to this approximate, unconstrained penalty method expression.
All right, so here we are in MATLAB, and this is a very similar script to what you've seen in our previous videos when we were talking about using the optimization penalty method, so I'm not going to spend a lot of time going over it. As you can see, we have our standard initialization where we basically pick a initial guess at what we think the decision vector or the optimal solution is going to be. So in this case, what we're doing here is, you can see I'm just using a whole bunch of zeros since I don't really know, although I do know that since I want the vehicle to be flying forward at 85 meters a second, I think the component U is going to be pretty darn close to 85, so I'm making the first element here 85, which is basically saying, yeah, the U component, or the forward velocity component along the body x-axis, is going to be near 85. We're going to see later on it's not going to be exactly 85, but I think this initial guess of 85 and then all other zeros is fairly reasonable to start with. So let's start with that as an initial guess. Then what we'll do is we'll go ahead and we will throw the unconstrained approximate cost function here at fmin search and see if it can solve it. So let's just take a look at what this looks like, what the cost function is. And as you can see, it's nothing special. Again, we said that the cost function is really a factor or a function of z, right? These 14 decision variables. So I'm going to pass in a 14 element long vector. And the first thing I do is I break them up into x and u. And that's just going to allow me to call our standard RCAM model function, right? This is the function that we developed earlier that is, you know, a couple hundred lines of code. But what it basically does is it calculates at the end of the day the state derivative x dot if you give it x and u. Okay, so this is where all the magic and this is where all the complication comes in, is basically the dynamics of the aircraft are all captured kind of here in line 6. Then what I'm doing here is I'm just calculating a couple of these intermediate variables. You know, theta we said is going to be necessary in combination with alpha in order to calculate the flight path angle gamma, right? And one thing to note here is I call this thing gam instead of gamma. The reason why is if you look at gamma is actually a MATLAB function, so I've seen issues where if you call this variable gamma, it has a little bit of an issue potentially, so I would rename this to something else besides gamma.
Okay, so that basically gets us everything we need. Oh yeah, here's the airspeed. Like we said, we need to calculate the airspeed using our standard formulation. And then all I'm going to do is I'm just going to generate, I'm going to stack all of my constraints up into this vector Q. And then I'm going to go ahead and define my penalty parameter matrix H. And again, we're just using a diagonal matrix. And in this case, I'm using the same penalty parameter. All the alphas are going to be 1. If we had issues with convergence, we could start playing with these alphas, and we could make some of these constraints more important than others. Like if we really cared about the steady state rather than the straight and level portion, we could more heavily penalize the first 9 constraints than these other ones. But for now, let's just start with a diagonal matrix of all 1s and see how this works. And then all I do is I generate my cost function by basically taking Q transpose HQ. So that's the cost function. And then what line 18 and 19 are going to hopefully do is try to give that thing a solve, and we're going to try to solve it and find a minima of that cost function. Then all I'm doing right here again in line 20 and 21 is I'm going to break up that 14 element vector and get the x's and the u's. And the only reason why is I'm going to again copy some of that code that we saw in the cost function out here just so I can verify that the constraints are satisfied. So I'm going to take the optimal solution that fmin search kicks back, and I'm going to see, does the x dot actually come out to 0? Does the VA actually come out to around 85? Does this come out to near 0? And do all these other ones also come out to near 0? And then what I'm going to do at the end of this routine is I'm going to save my optimal solution of the optimal state and the optimal control, which theoretically should solve this trim point. And then if it doesn't solve it, I'll come back up here and I will reinitialize with the old values and start again. So let's just start and kick this thing off. Let's start here with an initialization of 0, and I'm going to run this here. Let's go ahead and hit run. And notice, yeah, this cost doesn't look great here, right? This is the optimal cost that was returned, and it's not near 0. So actually, this solution here is probably not optimal. And actually here, look at this. Fmin search even threw out a warning saying that given my settings here, how many function evals and iterations that I wanted to allow it to do, it basically, it bombed out. It didn't find a solution. So, that being said, what we can do is it did save those values here in the mat file. So what I'm going to do here is this solution here, as you look, it's pretty close to my initial guess here, but it's not exactly my initial guess. So it has started perturbing some of these other states and controls. So what I'm going to do now is let's flip this switch now to a 1, and instead of starting from this 0 location, let's start the optimization process again, but now use this location as my new start point. Okay, so if I run this again, aha! This is looking better. Look, the cost is going down. We're now e to the minus 5. Let's run this thing again. Well, bam, e to the negative 8. Let's keep going. Let's get greedy. Here we go. Now we're cooking. Look at this value. This is effectively 0. So now we've satisfied all the constraints. This solution should be pretty darn good. In fact, to convince ourselves of this, let's come here. Let me remove the semicolons on all of these lines. Right? These were all of the constraints, right? Here's the constraints 1 through 9, and then constraint 10, 11, 12, 13, 14, right? So let's just go ahead and see, are all of these things about where we want them to be? So if I just select these and evaluate the selection, here we go. Let's take a look. Okay, x dot, did we satisfy steady state? Is x dot equal to 0? Look at this. It's 10 to the minus 9. I would say yes. This is pretty darn close to 0. So we did satisfy the steady state constraint. Let's go ahead and see, did we get the airspeed right? Look at this. Bam, right on. We got the airspeed of the aircraft. It is flying at 85 meters a second. How about the climb angle, right? Or the flight path angle? Yep, that looks like 0 to me. Looks like there is no crabbing motion, no sidewards component to the velocity. So we should have a side slip angle of basically 0 here. How about phi? Yep, the wings are level, and look at this. The psi is also 0, so we're heading north. So long story short, this solution right here looks really, really darn good. So let's examine this a little bit. So the first 9 of these should be the state, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so look at this. it looks like, yeah, the U component is near to 85, but there's definitely a W component. So the aircraft is actually at a slight non-zero angle of attack, which again makes sense, right? Because the aircraft is flying along, the thing weighs 120,000 kilograms. You're going to need some positive angle of attack to generate the lift to offset the weight, right, at steady state. So that looks great. P, Q, and R, these next three, those should definitely be 0, and the solution kicks out that they all should be 0. Okay, that's awesome. Phi right here, we constrained phi. We said we want the wings, we want the bank Euler angle to be 0, so that's exactly what it came up with. And here, look at this. The pitch angle, though, the pitch Euler angle is non-zero. So again, this corroborates our result here, where we said that there's going to be some non-zero angle of attack. In fact, this is probably exactly the angle of attack because there's no climb angle. So again, the aircraft has an angle of attack of 0.015 radians and no psi here. So the aircraft is flying due north. Now let's look at the next 5. These 5 are the control inputs. So the first one, this is the aileron. Again, this makes perfectly good sense. We shouldn't have any aileron if we want to be flying wings level. But we need a non-zero, and actually this is a non-trivial amount of tail surface deflection to get us the angle of attack we need. We need 0 rudders. And then here's the other thing that's interesting. Look at both of the throttles. The 2 throttles are matched, right? Which again makes pretty good sense for this situation. So again, this solution looks pretty darn good. So with that being said, why don't we jump back over to the board and have a little bit more discussion on the results that we get.
All right, so we saw that the FMID search basically got us this solution for a trim point. And I just wanted to write it up here and have a little bit of more discussion about kind of the difference between the trim and the equilibrium point, as well as our constraints. Now that we have a solution, we can kind of understand this. So again, a lot of this makes good physical sense, right? We saw that there's no aileron and no rudder, for example, here, and the engines are matched. They have the same throttle setting in order to get a straight and level flight. Now, one thing that I've seen in the past is a lot of people have asked, why didn't you just add that constraint a priori? Like you knew ahead of time, right? Why didn't we just say over here, like I can put the aileron here as a penalty function, as part of the penalty function, as part of our constraints, right? You intuitively know that there should not be any ailerons. And same thing, why not add, like the rudder should be equal to 0, and then maybe even say that, the throttle 1 minus delta throttle 2 has got to be equal to 0. Basically saying that the throttles have to be matched. So you could add these constraints, added constraints. So a couple of things to note about this. First off, there's nothing wrong with adding or removing constraints from our optimization problem, right? We saw that in some situations, even if you have a problem that's over-constrained, the numerical algorithm can handle this, and it will try to trade off which ones matter more in terms of the ones you want to violate the least. These are all consistent, so we know that it should be able to solve even this over-constrained problem because all these equations are consistent with a feasible solution. Now, the one thing you might want to, I don't want to say worry about, but you might want to think about this. If you think about what we're doing right here, you're using your knowledge of the system and saying that I know that the aircraft is symmetrical and has all these good characteristics such that I'm pretty positive at the end of the day that the ailerons and the rudder have to be 0 and the throttles are going to have to be matched in order to get me this straight and level flight. Now, what if that wasn't the case? What if your aircraft had some, or your model had some asymmetries in it, right? Maybe one engine was bigger than the other, or maybe it's an aircraft configuration which is not symmetrical about the XZ plane, like you might have an engine on one side and then a sensor pod on the other. So if you did this, when you add these constraints, in some situations, you might make the problem infeasible. So in general, I think it's safest to basically take these out and leave the problem as sort of add as little constraints as possible and allow the optimizer the wiggle room it needs in order to find solutions, okay? So maybe that's one thing to note. The other thing I want to talk about now that we've kind of got a good idea on the trimming and the equilibrium points, let's talk, there's a little bit of a difference and a distinction. A lot of times people will use the words equilibrium point and trim point interchangeably, and they appear to not be any different. I do want to call out that there is definitely a difference, right? So an equilibrium point is typically, its equilibrium points are like a subset of trim points, okay?
equilibrium points are basically a trim point. A trim point is just saying I want the system operating in some location, right? I want to find a location, an X and a U, that correspond to some interesting behavior, right? In our case, it's straight and level flight. Now, the thing that makes it an equilibrium point, as we talked about earlier, it's basically these set of constraints, right? If you satisfy the condition that X dot is equal to 0, then you have an equilibrium point. So an equilibrium point is definitely a trim point, but a trim point is not always an equilibrium point, right? Going back to our aircraft example, as a very simple case, what if the aircraft was in a steady coordinated turn, right? All it was doing was banking and turning and doing something like this, right? This is an interesting trim point that we want to solve, that we might want to solve for. And in fact, we will later on down the road. We'll go ahead and throw this numerical optimization scheme at trying to find the trim point that is associated with this steady state coordinated turn. But as you can see, it's definitely not an equilibrium point, right? The states are not all equal to 0. In fact, right, psi is going all over the place. A couple of these other things are non-zero. So that is not an equilibrium point, right? Where the aircraft is flying around and around in a circle. It's not an equilibrium point, but it is a trim point. It doesn't really matter. The numerical optimization routine doesn't care if you have an equilibrium point or a trim point. We can follow the same approach and tackle both of them using this framework. So I think that's another point that I wanted to make here. Okay, so that being said, maybe what we should do right now is, okay, the routine kicked out a value. How do we know that this is actually going to work, right? We should probably run over to Simulink, use this as an initial condition, use this as a constant control input vector, the Simulink model, and fly it around and verify that it does fly steady state and straight and level. So let's jump over to Simulink and do that right now.
All right, so I've just whipped up a quick MATLAB script to basically load in the optimal trim point that we just solved for and then use it to drive a Simulink model. So let's just take a look at that Simulink model. And as you can see, all we're doing with the Simulink model, here is the RCAM model that we developed in one of our previous lectures. Again, this is our aircraft, which takes in the 5 control surface deflections and computes the 9 states. And if you look inside here, all we're doing is we're basically setting this X star to be the trim point that we just solved for using the numerical optimization routine. And then what we're feeding in as control surfaces are just the constant U star values that are coming in. So let's run this sim for 250 seconds and then just plot the states and verify that this thing is flying in steady state, straight and level flight. So if I just run this script, you'll see it'll execute the simulation and then just plot all of those 9 states for us. Let me pull this over to the window. And as you can see, look at the scales on this. This looks like it's going pretty well to me. Look at this. It stays at a pretty darn close to 85 meters a second in the U, and then a little bit in the V component, but everything else is 0 where it should be, right? And again, look at these scales. These scales are a little bit misleading. It looks like this is changing, but really psi is not changing, right? It is basically staying at 0. So I think this is a good validation showing that the system is working and that solution we found is flying along straight and level at the desired trim condition. Now, what's interesting, and maybe the next question that's on your mind is, okay, it's flying along and everything is hunky-dory, but what if we hit some kind of perturbation? What if there's like a gust of wind that knocks us off of this trim point? Will the system come back to this trim point? Well, technically, that's a discussion for another video when we start discussing linearization and linear analysis about this trim point, but since we're here in Simulink, I think this is a real quick, easy addition to make to the model. Let's come here to the model, and I will actually just copy in a block that I've already prepared, and let's wire this in right now in line with the input. So what this perturbation block does is if we look underneath of it, you see that right here, all we're doing is we're perturbing, I guess in this case, we're going to give it an elevator kick. And all I'm doing here is I'm going to kick the elevator, or I guess the tail surface, by 5 degrees, and we're going to do it for, looks like for 1 second, okay? So if we go ahead and run this again, let me save the model. All we're going to do is we're going to fly along straight and level for 5 seconds, and then we're going to hit the tail with this doublet for not a full doublet, but a pulse for just 1 second and deflect it for 5 degrees. So let's run this again and see what it looks like.
And maybe instead of me explaining what the scope should look, or the input should look like, let's just look at the scope I've got here. So again, let's pull this over. And as you can see, yep, we are just using the trim values of the control, except for at 5 seconds where I hit the tail for 1 second with this 5 degree pulse. And here is now the response of the system. So again, it looks like we're flying along hunky-dory for 5 seconds, and then we whack the tail surface. And look, we excite some modes, but it looks like the vehicle does come back, and after, 4 minutes or so, it looks like it starts settling back to a trim point. Now the question is it the same trim point that we started at? Did we go perturb it to a different trim point? Again, like we said, that's going to be coming up in a future lecture where we're going to look at that in a more rigorous fashion. But, since I'm here, I can't resist. Let's do something different. Let's go ahead and let's pulse the ailerons now, right? Because if you look at, let me flip back to this figure. This was the results when we pulsed the tail surface, right? The elevator effectively. And look at this. The V component of velocity stays at 0. P stays at 0. R stays at 0 here. Phi stays at 0. And so does psi. They all stay at 0. So this elevator or this tail surface pulse seems to only excite and create motion in the longitudinal states, right? Which again makes sense because this aircraft is symmetrical. What I want to do now is let's switch this. Let's pulse instead the ailerons with that same kind of input and see what happens. So I'm just going to switch that pulse now to the aileron channel and save this. Run the model again. And again, let's go look at the scope of the Simulink model just so we can see what it looks like. And I'll pull this up. So again, yep, so we're just flying along again, straight and level, and then at 5 seconds, instead of hitting the tail, we're going to pulse the aileron for a little bit. And now, here's what the results look like. And now you see we actually excite and create motion or state trajectory movement in all of the channels in this case. And now at the end of the day, you're no longer flying due north after this. You're flying at some alternate heading, which again makes sense. So this is actually pretty darn interesting. And again, I got a little excited here, and we're now talking about a topic that is a little bit off course from our current discussion. But I wanted to show this and kind of whet your appetite because we will get to this linear analysis shortly. Now, maybe though, getting back on topic, the last thing that we can do is, since we've got our Simulink model here, you'll recall in one of our previous video, we also talked about how you could trim a model using Simulink. So let me go ahead and let's do that right now. Let me go ahead and make a few small modifications to this Simulink diagram, and I'll be back in just a second. All right, so what we want to do now is we want to see if we can use MATLAB's linear analysis tool to go ahead and perform some of this trimming operations for us and see if we get the same results. So what I've done is I've modified the Simulink diagram to make it appropriate for that type of analysis. We've got our same aircraft model right here, right? This is the plant model. But now instead of having a constant input, I've just muxed in a bunch of these input ports to represent the 5 different inputs, and then I've calculated a couple of outputs that are based on the state, and these outputs are the airspeed here and the flight path angle gamma. Again, these are the 2 additional outputs that we want to put constraints on, and then I've routed those here to output blocks. So with this model in place, what we can do now is we can go ahead and do the same thing that we did in our previous video. Again, if you're unfamiliar with using the linear analysis tool to trim the model, please check out our previous video. I'll leave a link to that in the description below, or you can click on the card in the upper right to get to there. But we're going to come here to Control Design, Linear Analysis, and let me drag this over to the same screen. And then what we can come here is say operating point, and I'll say trim model. And what we can now do is start specifying the appropriate constraints that we did earlier. So same thing, here we go. Here's our 9 states. Yes, we all want steady state constraints. So this here, putting check marks in this column is basically like saying x dot 1 through x dot 9 have to be 0. So we're basically looking for an equilibrium point here. Now, the inputs, we are going to leave these as unconstrained because, like we just talked about, I don't necessarily want to constrain the aileron or the rudder or the throttles directly because I don't know if I'm going to need some non-zero deflections here to trim out the aircraft. So the outputs, though, I do want to constrain these. Namely, the first one, the output is VA. I need that to be constrained to 85, and I need the flight path angle to be constrained to 0. So with that being said, I think we've set up all the necessary constraints, and we can now use the linear analysis tool to perform a very similar trimming routine. So if I start trimming, hey, look at that. It says the operating point specifications were successfully met, and they're stored here in OP trim 1. Let's go ahead and look and open this up and take a gander. Here's what we end up with as a solution, and look at this. This looks really darn close to what we had earlier. In fact, gosh, I wish I had that printed out someplace that we could kind of compare left and right. I guess I kind of do. Let me see. I wrote this down in a notebook over here. So we can see that the trim, whoops, let me see if I can get everything on one page so we can stare at them. Yeah, look at this. X1 matches X1. All of these seem to match up quite nicely here in terms of the states. So this is giving us the same solution for the states. How about the input, the control vectors? So yeah, no aileron, a non-zero tail. Again, this is here is in radians, and that's the only difference why I printed my, wrote my answer down here in degrees, but those are the same number. Minus 10.2 degrees should be the same thing as minus 1.78 radians. Here, no rudder and matched controls. So look at this. This is great. So here's another way to skin this cat, right? Instead of using our own hand-rolled optimization scheme where we use the penalty method and use fmin search to find it, we could use the Simulink MATLAB linear analysis tool to perform a similar trimming operation. So, with that being said, I hope this was interesting, and it sets the stage for our next discussion where now that we have our trim point, we can now start thinking about linearizing the model about this trim point so we can start answering questions about, is the system stable? What do the poles look like? What's the dynamic response? All of that kind of good stuff is now within reach now that we have a trim point. So, I hope you'll join us at that future video. So, with that being said, I think now's probably a good spot to leave it. If you enjoyed the video, I hope you'll also consider scrolling down a little ways and clicking on that subscribe button. It really does help me continue making these videos. And if you have any ideas or comments, please leave a comment below. I really like to hear from everyone, and it's a good place to get a discussion going amongst like-minded individuals that are studying this topic as well. So until I catch you at another video, I think I'll sign off for now. I'll talk to you later. Bye.